Good morning. Homework 6 will be posted very soon, and it will be the final homework of the quarter. Homework 6 will cover everything that I'm going to talk about in the remaining lectures. The remaining lectures will be, there will be review, but the new topics that I will cover will be like kind of weird, kind of advanced optimization strategies that either tools will use or people used to use back in the day, kind of historic things that are still totally asked about in maybe interview questions if you wanted to do this sort of stuff, or maybe you will have to demonstrate your knowledge of this if you have to implement your own tool, like if you want to work in synthesis. Learning about these kind of advanced optimization strategies are important. So, okay, that is the hook for today. So I wanted to pull up this page, which is not quite relevant to the topic, but I think it's still maybe important to be aware of kind of when pop culture, when coders enter pop culture, I would say. So has anyone seen this article before? Whoa, okay, almost none of you. This is crazy. So this was extreme, this like shut down like the world in 2021. Like that was more important than COVID, I feel like. So basically some person was like really angry about how long it took to load GTA Online. It's a video game. If you've played it, it takes a very long time. And they're like, oh, like why does this take so long? And basically they ran this tool called a profiler, and they found out exactly what code in like GTA's code base was taking so long to run. And so they figured this out, and they wrote it on this little blog right here. And they were like, hey guys, like it's this part of the code that's taking really long. And then they fixed it, they made it faster. And then because of that, they went super viral. And the company Rockstar, who created GTA, like paid him a bunch of money. And now, whatever, just because like he profiled this code, he was able to become like super famous. And then he also, he fixed runtime, or the loading time for a bunch of people. But okay, so for the two people in this room that have seen this article, does anyone know what the thing he had to optimize was? Yeah. It is he found that it was spending like 50% of its time in JSON parsing. Okay, anyone heard of JSON? Okay, I was also hoping that would be higher. So JSON is probably the most common file format for storing data nowadays. It runs the internet. There's like random statistics out there that's like whatever, 2% of the entire internet traffic is like all just whatever JSON, or whatever, 50% of, I don't know, there's like some statistic, I don't remember what it is, but the emphasis is that JSON like completely runs the world. It's probably the most common file format for storing data. And here is kind of just an example of what JSON looks like. So it's a very basic file format. It's kind of in the same form as like a Python dictionary, if you are familiar with that. So you have brackets right here, and then you have strings to denote a key, and then you have a colon to denote a value after that. So the idea is that someone later on could write some sort of JSON parser, and then maybe they could say like whatever, JSON object. I guess it's getting angry at me because wait, can I do, let me just do this. Okay. Okay, so maybe you would do like JSON object dot like get or something, or maybe you'd say JSON object of, and then you'd put in like whatever value you want to get. And then so by doing this, now you would get whatever value is here. And so this is really great if you wanted to like pass an entire dictionary to someone else's computer. So this is a very small JSON file, but you can have JSON files that are like gigabytes long, and you can send like entire like databases, and really powerful. Okay, if you haven't seen this before, now you've seen it. Okay, good. You may notice that the syntax for this is fairly straightforward. So it looks like you just have a single curly bracket, and then there's some like white space, and then it expects some string, then we have a colon, then some value, then comma, and then it repeats, and then finally at the end, then there's like a close bracket. Okay, so if you were writing a program to parse JSON, what would you probably take from this class to implement a JSON parser? Yeah.
Would you have like something that's iterating through every character, and then like a mux that's saying like if you have a comma that separates it or like stores it in as well?
Yeah, so you probably wouldn't use muxes. That's a very kind of hardware-y topic. So if you would take a step up, even past that, the answer I'm looking for is state machines. So language parsers, all language parsers, not just JSON language parsers, but everything, C++, JavaScript, anything, they all rely on state machines. And this is arguably, in my opinion at least, the most common use of state machines is specifically for parsing out the language, parsing out language constructs. So for example, here is json.org. So this is the official JSON standard that tells you how to implement JSON in a standardized way. And right here, we have basically a state machine bubble that it gives us. And this is how it tells us how to implement a parser to parse out JSON. And it is not super crucial that we look at every single step, but you can kind of just see like, okay, so it expects a curly bracket, and then it has optional white space, and then it can expect another curly bracket at the end. That means like it's done parsing. You can also go to this like state, and in this state, like it's parsing a string, and then there's optional white space, and then parses a colon, parses a value, and then we can choose like, okay, do we go to this state next, or do we go and repeat? So so this is a state machine, and every language parser is just a state machine. And so because of this, okay, so it's coming full circle to where now it suddenly starts to benefit us a bit. There are a lot of optimization strategies that have been thoroughly researched on optimizing state machines, which is good for us because hardware also uses a lot of state machines. Because like maybe you want to be handling all these ready valid interfaces, and you want to be accepting in multiple inputs coming in and sending out multiple outputs and reading serial data. State machines completely run the digital circuit world. And fortunately, state machines are extremely popular in other fields as well, so they are highly researched, and so there are a lot of optimization strategies. Okay, cool. So hopefully this kind of paints a big picture. So it's really great that we are able to benefit from this this research topic. Okay. Now I want to show you one of the most popular forms of state machine optimizations. All right. So assume, I don't know, maybe we took the JSON state machine, and maybe we've reduced it down into this or something. So this is a state machine, state and transition table. So we have all of these states, so A through F, and then we have this output Z. Then we also have all of these next states here, and with X being 0 and 1. Okay, so I wonder if we can kind of squint our eyes at any of these states and realize, well, hang on, it looks like a couple of these states are actually like identical. Like if we look at this, maybe we could just remove an entire state. And if we remove one of these states, then in that case, like if we reduce it enough, then we could probably also reduce the number of logic gates, or maybe the number of flip-flops that we have to use in our design. So if we can just remove entire states, like if we can see that maybe two states are exactly equal to each other, and then we could probably just remove a state, and then potentially we could have a more reduced design. So spend 1 minute, see if you can squint your eyes at this, and decide if there are any states in this state machine that are exactly identical, meaning that if you start in that state, then your behavior throughout the rest of the state machine will be the same as if you started in another state. All right, begin. I'll give you 1 minute. Anyone notice any states that look similar? Yeah?
A and B's.
What was that?
A and B's.
Yeah, A and B. Well, it looks like if we start in A or B, no matter what, with whatever value we pass in for X, we will always go to the same next state, and also Z is the same. So because of that, it looks like we can probably just get rid of B. And then every time that we talk about B, now we could probably just replace this with state A. So down here, so this is state A. Down here, this is state A. All right, cool. So that's good. So we potentially reduced some logic there. We found some overlapping states. Anything else? Any other ones? Yeah.
Now with this new optimization,
C and F? Okay, yeah, it looks like we have 1 and then A and F, similar 1, A and F. Yeah, perfect. So we can get rid of state F and replace it with C. Cool. So now we've gone from 6 states to now only 4 states. So we've removed a flip-flop, so that is great. Are there any more states that are the same? Doesn't look like it. Look, how can we be certain though? Like, how can we really be certain? Well, let's take a look. So for state A, let's redraw it out. Actually, I think that'd be helpful. Okay. So. Okay. Good stuff. Okay. There we go. Okay, so here is our reduced state table. So let's just double check that there's no further optimizations that we can do. So can it be possible for A and C to be equal to each other? Why can A and C not be equal to each other? They have different Z's, yeah. So if but notice what if Z now was 1 for both of these? Would A and C be equal to each other? They would, yeah. It's kind of interesting though, because this one says it goes to A, this one says to go to C. But if A and C were both equal to each other, then we would just say like A goes to A goes to A, and it'd all be good. But since Z is different for both these, we must say that A and C cannot be equal to each other. Okay, but A and D, well, these have the same Z output. So, well, maybe they're equal to each other. So let's assume that A equals D. Well, if we assume that A equals D, then now we must assume that all of their states, their next states, must match as well. So we must assume also that A equals D, but we are already assuming that, so that's good. But then we have C equals A. So if A equals D, then C must equal A. And can this happen? No, we just proved that it cannot, so therefore there's a contradiction, so therefore A cannot equal D. Okay, and now can A equal E? No, it cannot, because they have different Z's. Okay, good. Now let's check C and D. Can C and D be equal? No, because they have different Z's. Okay, thank you. And can C and E be the same? Well, maybe. Okay, so let's do C equals D. Okay, and that would imply, C equals E is what I meant to say. So if C equals E, that would imply that A equals D. Can this happen? No, we proved up here that A equals D causes a contradiction, so therefore this cannot be equal. Okay, so we have checked every single possibility. This is the most reduced possible state machine that we can get out of this. Cool. All right, we're going to do another example. Yeah, we'll do this one. All right, spend 30 seconds on this. So I think this one's a little bit trickier, right? So, okay, so starting out, let's just try checking things, see what happens. So can A equal B? Maybe. Okay, so let's just see. So if A equals B, then what is implied from this? Okay, so that would mean that C would have to equal E. Do we have a contradiction? Not yet. Okay. And in fact, now we can look down at C. So if C and E are equal to each other, then what would that imply? Yeah, that A and B are equal. Okay. So do we have a contradiction? No, yeah, and actually we're even assuming that they're equal. So actually we're good here. Okay. Also from A equals B, what's the other thing that needs to be implied? Okay, D equals F. Okay, do we have a contradiction there? Yeah, not necessarily. And actually, it looks like C and E are equal, and we are already implying it up here. So actually, we have a closed loop of reasoning. Therefore, every single one of these assumptions was true. There's no more possible paths that we could make. Every single path that we took ended up not causing a contradiction, and there we go. So now we can come in and reduce this significantly. We can say that F is done, and E is done, B is done. Yeah. Did I mess this up? No. Okay. Can we go further? So let's now check. So can A and C be equal to each other? No, because they have different Z's. Okay. Can A and D be equal to each other? No, they have different Z's. Okay. Could C and D be equal to each other? Maybe. I don't know. Okay, so let's check C equals D. That would imply that what? That would imply, yeah, that A equals C. And can this happen? No. Therefore, we have contradiction. So our initial assumption was incorrect. And it looks like this is the most reduced that this state machine can get. All right. Cool. We're going to do one more. Yeah, question.
What can we do with the D in the A row, like for where x equals 1? Because we have D equals F with both D and, or, sorry, I lied.
Yeah, sure. Right, so if this D instead said F, then yeah, I would replace this F with D. Yeah. Okay, yeah. Good stuff. Okay, big one. Last one. Okay, so I'm gonna kind of walk through it. Feel free to watch this, or you can feel free to keep going with what you're doing. All right, are we still working? Going good. So I want to show you the first reduction that I made. So I noticed that A and B cannot be equal to each other because that would imply that D equals F, and D cannot equal F because they have different Z's. But then I went to the next value, which was A equals D, and I found that A equals D did not cause any contradictions, and also at the same time I was able to find that E equals C. So I was able to cross off both E and D, in this case. So then I was going to continue. Yeah, question?
Yeah, just a question with this table, like,
Yeah.
makes sense, because if is the first D where which state it goes to when C is 0?
Say that again?
Like, are those the transitions that it goes to, the D and E?
So, are you talking about these D's?
Yeah.
So these D's that represents the D input of the flip-flop. So it's also what will be the next state when you receive a pause edge.
And that's based on X or Z?
X. Yeah. Z is a separate output.
Oh, so Z is the output.
Oh, Z is the output. Yeah. 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 Thank you. Yeah. Yeah. Question.
Would you also be able to make A equal to H?
A equal to H. Yes, you could, because we can see, so A and A, C and C. Yeah, so these states immediately are equal to each other. So let me write that down. Yep, thank you. A equals H. Okay. Now we can get rid of all the H states. Okay. And good, so it looks like that is all of the zeros checked now. So let's now check the ones. So let's see, so can C equal F? So let's check. So, so here we have C equals C, so that is already true. Then we have A equals G. So if C equals F, then that means that A must equal G. Can this happen? No, cannot. So therefore, C cannot equal F. Okay, and then let's check. So can C now equal G? So if they're equal, then we have C equals C, which is fine. But then we have A equals F. And can this happen? No, it cannot, because they have different Z's. Yep, okay. So it looks like this is a fully reduced table now. Okay, yeah.
Can F and G also be the same?
Oh, thank you. Let's double check that. Cool, okay. So F, let's assume that F equals G. So that would imply C equals C, but that would also imply that F equals G. Okay, so are these equal? Yeah, looks like we have reached a loop. So yes, so these are equal. So every instance of G I could then replace with F. Cool, yeah, thank you. Good. Yeah, and nice, now we only have 4 possible states, so we have in fact removed an entire flip-flop from our design, which is, yeah, always a good thing. Cool. All right, yeah, kind of makes sense. This is, cool optimization strategy. I will say it's not too popular in digital design from what I've seen, primarily because the number of possible states that we work with is maybe at most like 16, and even that's like a large truth table, having 16 whole states. Generally, digital designs don't deal with really large state machines anymore. In fact, if you increase the number of, if you have a system that requires like a really large state machine, you would probably instead just use a different type of circuit. Can anyone guess what type of circuit you would use if you need something that can do a bunch of different like sequential operations one after another? what is like the main circuit? Yeah.
Just a processor?
Yeah, you'd use a processor because CPUs, processors are so cheap that it would probably be cheaper to just use an entire CPU than it would to spend the engineering time to develop a state machine. It's kind of interesting. You can just pull in an entire CPU, write some C code, or even write some assembly code, and then throw it in, and you're done. So actually, for the most part, you don't really write very large state machines. However, you absolutely do use huge state machines for languages. So this is a more popular optimization strategy that is used in language parsing, but it's all done super behind the scenes. Like if you write a language parser, anyone created their own language before? Okay, I'm sure you will. It's an absolutely crucial skill, very common that you will just need to create a language for a very specific problem that you need to solve. It happens all the time. So yeah, definitely take whatever compilers or languages classes they offer here because it will definitely benefit you. Yeah, so if you write a language parser, then you probably write it in like this nice format using Bison and Flex. Those are GNU tools. And then then Bison and Flex will optimize it and turn it into a nice state machine, which will have all these optimizations applied to it. Yeah, okay, so that is the primary purpose of state machine reduction, but it's still in every single digital design textbook on the off chance that like maybe one of you at some point might need this random state machine optimization strategy. Cool. Okay. Yeah, any other questions? I'm going to move on from this specific topic to a completely different optimization strategy. So yeah, any final thoughts on this? Yeah, this will be on your homework and on your final. There will be just like a basic question that's like, oh, like reduce this to the minimum number of states. Shouldn't be too tricky. In some are like 85% of the class got it correct. So, yeah, question.
So what did you fix in the JSON parser that made it so much faster?
Yeah, oh, great question. It actually has nothing to do with this. I think it was using like recursion or something when it shouldn't have. I actually don't know. Great question. Feel free to look into it, make a Piazza post and let us know. Great question. I do not know the answer to that. Yeah, okay, so speaking of kind of cross-domain algorithms, have people heard of the extremely famous problem P versus NP? So I should have researched this ahead of time, but in the past 50 years, there was an initiative to grab all of like the hardest possible problems that we were facing in the world, like math problems, logic problems, created a list of them. On one of those was the Riemann hypothesis, and P versus NP. You can solve any of these problems and you get $1 million. Pretty great. P versus NP. Okay, so let's talk about this problem though. It's very important to us as computer engineers, computer scientists, electrical engineers. So the idea with this is there are classifications of problems in the world. For example, a problem may be sort this list. Okay, so sorting is generally a pretty easy problem. Right? We can write a naive algorithm to solve that in O of n squared time. We could also write an algorithm to solve in like n log n. So like I'll just say, so sorting to solve. And then how long does it take now to check whether an array is sorted? Oh, also, have we heard this O of n squared notation before? Okay, good, yeah. Anyone not heard of this yet? Okay, so I'll just say, so O of n, this is saying it is a rough estimation of how long your algorithm takes to run. So if I have if I just have a loop that's like like 0 to 1 or 0 to n, right? So we would say that this would run for like O of n time, because it takes like n, there's n operations in this loop, so therefore as you increase n, it will effectively take about n time to run, versus if I now added another for loop, so if I like nest them like this, then now for every single for loop that is run, now you need to run an additional for loop, so it's actually like n whole for loops, meaning it's n times n operations. So this right here, this would be n, or O of n squared. Okay, hopefully that makes sense. Yeah, question?
That's called time complexity, right?
Yes, exactly. Yep, time complexity, correct. Okay, so yeah, I'll just say that, time complexity. Okay, good. Sorting, now, yeah, okay, so how long now does it take to check if an array is sorted? N, perfect, yeah, so check if an array is sorted in O of n. Yeah, really easy to check this. There are a lot of problems that have this property where they both have an algorithm to solve them, and they also have an algorithm to check whether it is solved. So there's the two separate things here. Okay, this is the classification called P. And I'll say it's deterministic in polynomial time. Okay, meaning it can be verified and can be solved in polynomial time. Polynomial time meaning it's like O of n squared, O of n cubed or something. Something kind of reasonable, something that will end in our lifetime. Now, there is another classification. Actually, I'm gonna reorganize this just a little bit better. Say this is O of n, time complexity. Okay, just trying to make it a little bit clearer. So this is n squared. Okay, good. Now there's another classification of problems called NP. And NP means it is not deterministic in polynomial time, meaning that it is, actually, let me be a little bit more specific here. So NP complete, this is a subset of NP. Anyways, okay, cool. So what this is it takes O of n to like some number, so we'll call it like n to the k, so some polynomial amount of time. It takes n to the k to verify, which is fast, but it takes O of a to the n to solve. Okay, which one is faster? O of n to the k or a to the n? Which one is faster? Yeah.
N to the k?
Yeah, n to the k is going to be much faster because that's just a generic polynomial. When you have a to the n, this will explode extremely quickly. So if we just have like basic numbers here, like if maybe we plug into like Desmos. So if maybe we have a reasonable constant that's maybe like maybe we say that a is like 30 or something. So maybe we need to do like 30 like operations per n, but then it's exponential. Then now we graph this. You can see like very, very quickly. Like if we only have just a few, so if I say f of x is equal to this. Okay, so if I say f of, and I want to plug in maybe like 100 elements, right? If I have maybe 100 element list that I want to sort using this NP complete algorithm, well, you can see that this is a huge number. And so this is not a feasible like algorithm. Unfortunately, yeah, so if it takes this amount of time to solve, then no matter what, like we will not be able to solve these problems. So that is kind of the whole thing here, is that there's a classification of problems that are easy to solve, and then there's a class of problems that are impossible to solve. And inside of this NP complete category, there is something called satisfiability, and I'll shorten it to SAT. Satisfiability. Cool. Okay. Satisfiability is basically just sum of products, product of sums, Boolean algebra simplification. So that's unfortunate, right? What does that mean for us digital designers? So if we have a large like digital circuit, what does that mean for us? Yeah, anyone? Why are we sad that we are in NP complete? Yeah. Well, it'd be nice if, given a Verilog circuit, if we could find the most optimal implementation of that, right? And satisfiability, that's basically all this problem is just like, yeah, like can we, like how do we solve this like circuit, basically? And we can't do that. So we're very sad about that because now we are like actually bounded, like we cannot find the most efficient implementation of these. And I bring up this all these like proper nouns and things because you will definitely see this throughout your life. Some of you have already seen this. This is another huge research topic. Like you will have entire departments that are dedicated to P and NP problems because there's a whole classification of problems that no one knows whether they are in P or NP. And if they are in P, well, that's great. Now someone can create an algorithm for it to run in polynomial time. If something is in NP complete, then they will be happy because then they know they can move on from that problem because it's not even worth their time to solve. So yeah, P versus NP, this is a huge algorithm question. You'll definitely see more of it. Yeah, question?
Does this imply that you can verify your Verilog circuit and end of decay? Like if you can't find the optimal solution because it's A to the n, could you verify that you have the optimal solution?
You can't verify that you have the optimal solution, but you can verify that your solution is a solution. Yeah, so given a solution, you can check whether that is maybe smaller than some threshold. Maybe it's like, oh, like can I design a circuit with less than 100 gates or something? You can just check like, yes, this is less than 100 gates. And you can also check like, does my circuit work at all? That's basically, yeah. But this is all leading towards, so in the 80s, I would say, computers became faster, which is great, but also computers became way bigger. And so there's kind of been this arms race of like CAD tools versus the computers that were designed with the CAD tools. So as computers have gotten faster, CAD tools have also gotten better. And as CAD tools have gotten better, computers have also gotten better. And in the 80s, throughout the 2000s, there was this big competition that everyone would enter, and it would be, who has the fastest SAT solver? Because it sucks that this is such a difficult problem, but we really need this if we want to make our computers faster. So over this many year period, there were all sorts of efforts trying to make SAT as efficient as possible. And so there's all sorts of SAT solvers out there now. So almost basically we consider SAT to be a solved problem at this point, even though technically in specific edge cases, no matter what, it will always be A to the n to solve. But for like a lot of the most popular use cases, we can actually find like a very optimized circuit. And so within this, there is an algorithm that I wanted to show you today that works very well to give you kind of an intuition of sum of products things, sum of products expressions, and also has been used extensively in a lot of the tools that was a part of this arms race that took place in the 80s through the 2000s. So this algorithm is called a Carnot map. Anyone heard of Carnot maps? All right, cool. So kernel maps were designed, or invented, I guess. Like it's kind of arguable who first created them, and they first appeared in a paper in like the 1800s, and then they became popular in the 50s, and and then were utilized by SAT solvers in the last few decades. And so what the purpose is given some logic expression, you want to be able to find the most reduced sum of products version of this. So that is the goal. So here I have this table here. So here is a Carnot map. And notice that, so I have A, B, and C, and D. So these denote all of the different possible inputs of A and B and C and D. So every square, this is saying, like if I look at just this square right here, we can see that this square denotes the case of when A equals 0, B equals 1, C equals 0, and D equals 1. And then in this square, we would either put a 0 or 1, depending on if this expression is true given this number. So just kind of looking at this, is this cell going to be 0 or 1? Yeah, why is it going to be 1? What was that? Yeah, we have this not A term right here. So since we have this not A term right here, we can very clearly see that since we have this 0 right here, this is going to be 1. Okay, well, what will this, oh, I already drew it. What will this one be? 1. Why? Yeah, not A. So actually, it looks like anytime we have a not A, which is all of these cells right here, all of these top 8 cells, they are all going to be 1. Cool, okay, great. Let's go through some of the other terms now. So let's check now C and D. So which region on this are denoted by C and D? Go and tell the person sitting next to you which bubbles we should fill in here to denote C and D. Yeah.
The top 1, 1 column?
Sure, yeah, so this 1, 1 column, it looks like in every single cell right here, we will have C and D. So yeah, we will have 1 and 1, okay. Let's now check this one. So what will this be? So it'll be A and not B, at least, so we know it'll be somewhere along here. And then will it be the left half or the right half? So it's going to be C equals 1, so I think it is going to be this part right here. So good, okay. And then there is this final one right here, AB not CD. Where will this be? Right here? I think, yeah. Yeah, because we have A, B, so A, B, and then we have not C, D. So not C, D. There we go. Okay, cool, so now we have this table. Well, maybe we can try to go backwards now. So we have this really nice table, but maybe instead of like starting with an expression, maybe we can ignore this and see, well, can we try to make terms out of this table? So I will copy this down. Okay, and also notice, so how many cells did we select for this term that had 4 whole entries, four whole variables? How many cells did we have to select? Yeah, it's just 1. Versus A, how many, or not A, how many cells did we have to select for this? 8. So it looks like the smaller the term, the fewer the smaller the term, the more squares that we need to select. So in order to reduce our terms to be as small as possible, we probably need to make our squares that we make as large as possible. So if we look at this, so what is probably a rectangle that we could draw on this to kind of like encapsulate a term? Yeah.
Top 2 rows.
Okay, sure, yeah. So the top 2 rows. So what term did this represent again? Yeah, this was just not A. So that was really easy. Okay, so we have not A. Okay, and then past that, well, we have this collection of 4 right here. What would happen if we selected all 4 of these? What term would this be? Yeah, so it looks like B is 1 for both of these cases, and it looks like D is 1 for both of these cases. So this square right here in the middle is DB. Okay, and then we have this little section right here. So what term would this represent? What I've just selected right there. So we know it's going to be, yeah, so we have to look at this. So we have A is 1, B is 0. So we have A, not B. And then which column is, what is the final variable to add?
C.
Yeah, then it's C. All right, cool. So there we go. So we've just reduced. So originally, we started out with this much larger thing, and now we've just reduced it to this. So that is the whole purpose of K-maps. Notice, though, I think we can actually do a little bit better than just this. Is there a way to make this term any larger? Let me show you kind of what I was thinking. So we can notice on this side, so when we have 0, 0, and 1, 0 on this top row and this bottom row, it looks like they only differ just by one single spot, right? They just differ by this A right here, but B is the same. So what we could probably say is instead of having this B term right here, or actually, sorry, am I doing this right? Let me draw it out. So what we can do is we can kind of like loop it around, kind of like this. All right, so like now it's like a larger square, kind of this tiled, it's tiled. So now we notice that this entire square right here actually represents not B instead of just A. Like we no longer care about the value of A here. Okay, let's do some quick little practice things. So if I have maybe 1, 1, 1 like this, then what terms do I need for this? Let's go and write this down on, go and write this out and then share with the person next to you. So if we have 1, 1, 1 up here, Okay. Also, so our rectangles must always be like in a power of 2. Like we can't just select all 3 of these. So I'm going to propose that probably our first rectangle should look something like this. And then maybe we have another rectangle that is just right alongside that looks like this. Because we can't make a rectangle of size 3 that would turn into a term. Because every term that we create, like if you just kind of look at it, you will see that every term, must produce like a power 2 square. So, okay, what would this yellow rectangle represent here?
Not A, not B, not C.
Yeah, so not A, not B, and then not C. And then what would this red one represent? So it would still be not A, not B. Yeah, and then it would now be D. Cool, so there's that. Okay. Let's now put a 1 right here. What is the new rectangle that we would draw for this? So would it just be like a 1 by 1 guy? It could, but that's not the most efficient way. Instead, we can probably wrap it around, do something like this. There we go. And it's totally fine to have a bunch of overlap here. Happens. Okay, so then what term would this one be?
Not B.
Not C, not B.
Yeah, perfect. Not B, because the 0 is shared on these, and then not C, not D. Okay, great. What if we had maybe a 1 right here and a 1 right there? So let's actually start from scratch, because I think that will create a lot of optimizations for us to do. Okay. What are our rectangles? Yeah, so we can easily select this top row right here. Okay. What is the next rectangle? Yeah.
There's gonna be like 2 rectangles that are like wrapped around, if that makes any sense, from like top to bottom, I guess.
So like this?
Yeah.
We can do better than that, because I think we can wrap this all into just one single rectangle. Yeah.
Around the sides to A, B, not.
Right, exactly. You can actually wrap it left to right as well. So instead of this, we can do this crazy thing where we just wrap every single corner. All right, let's write out the terms for this. So for this top row, what will this be? So it will be not A, not B for this top yellow term. Okay, and then finally for this green term, what will it be?
Not D.
Great. Okay, so we have not D that's shared on this, but then also in the in this side, what do we have? Yeah, it looks like not B as well. So it's going to be not B, not D. Yeah, pretty cool. Yeah, and this will give you a more reduced version than just doing, wrapping around just the top. All right, cool. So this is Carnot maps. There will be a question on your homework and on your final about this. This is an algorithm that has been used for the past, 70 years to reduce logic. And hope it's kind of interesting. Can save you a lot of time. Okay, great. Thank you. I will see you all on Monday.